Okay, we're looking at chapter 12 of Barnett's book, and we're in section 1, which talks about first derivatives and graphs. And the goals for this section are simple. We want to be able to identify increasing and decreasing functions, as well as local extrema. That's one goal. We also want to be able to apply the first derivative test, which is a major topic in this course. And finally, we want to be able to apply the theory that we learn in this section to applications in economics. So those are our three goals. Okay, so why don't we start by looking at increasing and decreasing functions, which your book does a great job explaining. Essentially, the big thing to get is theorem 1 in the textbook, and that's the relationship between a function f and its derivative, as well as the graph of the function. Wherever the derivative is positive, on any open interval a to b, if the derivative is positive, your function is increasing and the graph of the function is rising. If the derivative is negative, the function is decreasing and the graph of f is falling. As a very basic example, take a function you're well familiar with, x squared plus 6x plus 7, a quadratic function, and we want to find the intervals where this function is rising and falling. Recall that this the graph of this function is a parabola. So if we were to graph this function, we would get a parabola. However, without doing any graphing, we could just use the result of theorem 1 in the previous table and figure out where the graph is rising and falling. So what we do is take the first derivative, and the derivative of x squared plus 6x plus 7 is 2x plus 6. And then we simply check where is that derivative positive and where is it negative. Well, notice the derivative is positive or bigger than 0 whenever x is bigger than negative 3. Okay, we just solve the inequality by moving 6 to the other side. That's the step here. Divide both sides by 2. The graph is rising whenever x is bigger than negative 3. On the other hand, this linear inequality, 2x plus 6 less than 0, tells us when the graph is falling. So solving for x gives us x less than negative 3. That's when the graph is falling. Of course, if you were to graph this using a calculator or computer software or just by hand, you could easily see that up to x equal to negative 3, this graph is falling over here and then rises from negative 3 and to the right of it. Oftentimes when we work with these problems, a sign chart is very helpful. And a sign chart simply has the real number line, and it also has your derivative values. So you find the one value, negative 3 in this case, where we saw the cutoff. And we saw that to the left of negative 3, it was negative, the derivative. To the right, it was positive. We call this number a critical value. We'll talk about that in a bit. So wherever the derivative is negative, the function is decreasing. Wherever it's positive, it's increasing. Let's talk a little bit about this partition number, negative 3, also known as a critical value. Well, the partition number for the sign chart is a place where the derivative could change sign. Assuming that f prime is continuous wherever it is defined, this can only happen where f itself is not defined, where f prime is not defined, or where f prime is 0. Okay, so those are the cases that we're going to be interested in. So the formal definition is the values of x in the domain of f, where f prime equals to 0 or does not exist, are called the critical values of f. I want you to be very careful with this definition and notice one important key phrase. The values of the x in the domain of f. So you have to be in the domain of the function whenever you're considering x values to be critical values. Okay? All critical values are also partition numbers, as already mentioned. But there may be partition numbers that are not critical values. That's where your function itself is not defined. So if f is some sort of a polynomial, like the example we just saw, critical values and partition numbers are both the same. They're just the solutions of f prime equal to 0. Okay, so let's do a little bit more here. Let's do another example with a polynomial. F of x equals 1 plus x cubed. Once again, take the derivative, that's 3x squared. Set it equal to 0, right? This derivative is defined everywhere, so you don't worry about that. Just set it equal to 0, and that will give you your partition point at x equal to 0, your critical value. Then, on the real number line, position your critical value there, and check what's happening to the left and to the right of that critical number. Notice, if I plug in a number into the derivative, into f prime of x, that's smaller than 0, like negative 1, I will still get a positive outcome because I would get 3 times negative 1 squared, which is 3. Likewise, if I plug in any positive number, a number to the right of this partition point, into my derivative, 3x squared, I will also get a positive number because anything squared is positive times 3 is positive, so both sides are positive. What that means is that the function is increasing to the left and to the right of this partition point, x equal to 0. Looking at the graph makes this absolutely obvious. To the left of this point I'm increasing, to the right of it I'm still increasing. Let's take a look at another example here. F of x equals 1 minus x, the quantity to the power of 1/3. Or we could think of this as the cube root of 1 minus x, right? It's equivalent, this f of x, to the cube root of 1 minus x. You should confirm that the derivative of this function f prime is negative 1 over 3 times 1 minus x to the power of 2/3. Okay, having that in mind, once again we worry, where is this derivative 0 and where is it undefined? But notice this derivative is not ever 0, because if you think of it as a fraction can only equal to 0 if the numerator is 0, and my numerator is negative 1, so it's never going to equal to 0. So I only worry about where is the derivative not defined. And clearly you should see that it's not defined at x equal to 1, because this is where the denominator will be 0. So the critical value and partition point in this case is x equal to 1. Notice x equal to 1 is in the domain of the function. It is perfectly fine to plug in x equal to 1 into your function's variable x, and you'll get an output. So that's fine. So therefore, that's a critical value. We split the real number line into intervals based on our critical value here, our partition point. And what do we notice? To both left and right of 1, the derivative is negative. Therefore, the function is decreasing. Okay? So with that in mind, we move on to another example here. This one is f of x equals 1 over 1 minus x, a rational function. All right? F of x equals 1 over 1 minus x. Convince yourself that the derivative of this expression is 1 over 1 minus x, the quantity squared. So once again, a partition point would be x equal to 1, right? We see that. But notice, x equal to 1 is not a critical point. Why? Because this is not a critical point because it is not in the domain of f. This function, this point is not in the domain of f. If you plug in x equals to 1 in the original function, you will get an undefined value. In fact, we know from the graph that there is a vertical asymptote at x equals to 1. So this function has no critical values. We could still check, and we'll see that the derivative is positive on both left and right of 1. Therefore, the function is increasing. Remember, we consider points where the function is undefined as well when we do this test.